All right, so a couple things. Monday, there's some students from Mississippi State won some award, and their award is they're going to come to our class. But the Georgia saying, you can come to Georgia Tech. And then the college engineer's like, yeah, but what are they going to do? And then so it came down the chain, but eventually they decided they're just going to come to our class for their award. And Chris is going to take them out to breakfast, right? Right, Chris?
I think so.
Yeah. So these four poor students from University of Mississippi, they're going to come for this big reward, come to our class, which is on pretty much all math. They're not going to understand anything at all. They're going to come on Monday, and they would watch us do the quiz. So I have to move the quiz to Wednesday. Yeah. So we're going to do the quiz on Wednesday. What? They're undergrads. Yeah, they could. Yeah, maybe they might be help a little bit. So they're going to quiz on Wednesday, and we'll have the course project presentations on Monday. Who's presenting next week? Raphael. There's two Raphaels, isn't there?
Yeah, there were. Oh, yeah, maybe.
And Gaten?
Okay, it's possible.
Yeah, there are two Raphaels, which I found with project presentations, and so we'll have at least one. And I think there are three people who haven't presented yet. Cedric, Calvin, and
Did you mean course project presentation or journal?
Journal Club. Sorry.
You can start it kind of early.
Journal Club. But if you guys feel like you're ready, you can just do it on Monday. But if you're not ready, you could wait. But it's for a good cause, because otherwise they're going to watch us do math for like an hour. It doesn't have to be that good. But it'll be anything better, because I cannot, there's no way I can both satisfy the constraints of entertaining them and teaching you guys the stuff, because they're like, this is not a class for like them. Okay, all right, okay. So we'll have the other Raphael. Do I pronounce his name differently? How do I pronounce your name?
It's exactly the same way.
Oh, okay, all right, no wonder I'm.
It's like the male and the female version.
Okay.
Yeah.
So we'll have two course project presentations, and we'll talk a little about the homework.
I go Monday, right?
Yeah, they'll be both Monday.
Oh, two Monday.
Yeah, on Monday, and then after that, I'm just going to tell them to go walk around campus. Chris, you're going to have breakfast with them, right?
Yeah.
What did these
I bet they're going to give you Chick-fil-A. What?
win? Or what?
They won some big award, and their reward is to come watch us. I don't know. somewhere down the line, someone gave up thinking about this. Said sorry. But now it's our responsibility. And I don't want them to have a super bad impression. And there's some. Are they going to show up? What do you think they're going to? Is it really going to happen? Okay.
At least from the people I've.
Okay. All right. Let's see. Last time. Okay, we talked a little bit about unsteady irrotational flows. All right. We're going to we're going to basically apply potential. We looked at two unsteady flows yesterday. So let's go back a little bit. So unsteady and viscid potential flows. All right. So we looked at one of them with water waves, where you basically have the water surface sending these traveling wave information away, and you basically have these two boundary conditions, one the kinematic and the other one the dynamic boundary condition, which is basically the time-dependent Bernoulli equation, which we're going to use again to look at this added mass problem. Then we started talking a little bit about this idea of added, or I would say, sometimes people in the literature call this the virtual mass, but I think that was before they had virtual reality. This is a long time ago, so I don't think we can. I think it's really added, but you also get. It's not really. You can also. There's also this thing called fictitious forces in rotating systems like Coriolis, but I always kind of find those kind of like confusing, because this is actually a physical thing. So I'm going to call it added mass, but you might see it in the literature kind of elsewhere. And we said, hey, if you release a bubble underwater, the acceleration that it should travel as it goes upward, if you could just look at the buoyancy forces and the weight, you're going to get 1,000 times gravity, which is too fast because it's going to travel like 10 kilometers in a second. So we basically started calculating why. We said, why is it so much slower? And he said, physically, hey, this air bubble is rising, and this added mass this basically buoyancy calculation only looks at the forces on the air, but doesn't actually talk about what the fluid's doing. And in some ways, it considers the fluid to be kind of quiescent. But the fluid's doing a lot. In fact, it's accelerating, this little thing here, this ghost bubble was where the bubble was a second ago. And you can imagine, originally there was nothing there, or like air, and then we're pushing water there, and we're accelerating water into that space. And water is really heavy. So what we're going to be doing is we got to calculate how much energy it takes to accelerate the water into this hole, but also kind of like everywhere in the fluid. What's up? Yeah, that's kind of it too. You basically have this water going out of the way. It's kind of going to come from everywhere. But the idea is that this idea, our previous idea was basically U fluid was basically 0. We did not calculate anything. But when you actually calculate added mass, what we're going to do is take a control volume basically as r goes to infinity and look at all the kinetic energy in that volume. And we're going to estimate how much power goes into moving the fluid as we integrate it away from the bowl. And we're going to use these ideas that the speed of the fluid goes as 1 over r squared, which we calculated last time, or 2 times ago, this dipole idea. But we have to basically consider the motion of the fluid to really get how much you're slowing the bubble down. So in terms of like energy, this bubble is like you've got gravitational energy being released from the system, and that's moving the fluid into kinetic energy. And that's what we got to calculate. Because the previous calculation, there's no kinetic energy in this equation. It's just the energy of the air, which is like almost nothing. Okay, so that's what we're going to do. All right. So added mass. And to calculate this, we're going to do translation of a body in 3D irrotational flow. All right. So physically, we got some arbitrarily shaped body. Without loss of generality, let's just assume it's going in this x direction. So we got this velocity, which is going to be a function of time, velocity vector, because we got to have it accelerating. Okay, and then the position, the center of mass of this thing, I'm going to call x naught. I'm going to say x naught. The body's translating with the time. So this position of the body, we'll call this x naught, and it's going to increase. It's going to go to the right. Let's say. Okay. The surface of the body we'll call S like usual, and we'll have this. The reason we need to draw this normal vector, because eventually we're going to calculate the drag on this body by integrating the pressure along here, and we're going to use a time-dependent Bernoulli equation to integrate the pressure, which is kind of like a prequel to what you've got to do in the homework for figuring out that the cylinder has 0 drag. And we're going to be looking at the energy in the fluid all the way up to like really, really far away, which I'll call S infinity. Okay. So that's physically what it looks like. Conservation of mass. So this is conservation of mass, which is the only equation that we solve in irrotational flow, is this. And the boundary conditions. Now, just like we did before, the moving body. So basically, the velocity of the fluid, remember the fluid velocity is going to be dictated by this phi. So we'll say the velocity of fluid, which is gradient phi, is equal to the normal velocity of the fluid is equal to normal velocity on the body. This is not no slip. This is like no penetration on a moving body. imagine you have a moving wall. If the wall is stationary, it would just be equal to normal. But if the wall is moving, you got this n dot v, moving body. Okay. It's saying, and this is a statement of the fluid velocity, right? Because it got the phi there, and the right side is a statement of the body velocity. All right. And the second one is that, as we had before, that we need to have our velocities decay to 0 as r, let's call it x, goes to infinity. Okay. All right. So like we did last time, our solution is going to be, we have to contain the information of the moving body in it. The only difference is here, what we did 2 lectures ago was the body was moving at constant velocity. Here, it's just moving at some velocity change with time. So problem is linear in the velocity of the body. And the position of our fluid, the only position that we care about, I would say only matters, basically the position that we care about, relative to that of the body, which is given by x naught. Okay, because everything is kind of like in this moving coordinate frame. So our solution, the kind of solution that we're going to look at, is going to look like this. Phi, which contains our information of our velocity field, is going to be linear with the velocity of the body, which is a vector, and that this stream function is going to depend on where we are relative to the body. Right. Where again we've introduced this new kind of notation. We did this 2 lectures ago. We've got a stream. We talked about the Laplacian, this del squared phi. If del squared, we talked about these fundamental solutions. So you can put a scalar into here, you could put a vector in there, you could put a tensor, you could put lots and lots of solutions here because the right-hand side is 0. And in this case, we put what kind of like the solution that's the derivative of the scalar solution, which would be phi vector. Okay. It's just the same information, except it's basically contained in a vector. And that is not going to depend on x, that's going to depend on relative position of the body. So with this new solution set, this is kind of the way it looks like, we have a new governing equation and a new boundary condition. All right. You can imagine if I put this thing into del squared, because v is a function of time only, not a function of space. I'm still going to get the same Laplacian, except this is on phi vector. But the boundary conditions, we lose information on v because we contain them in the phi. So basically, the boundary conditions look like this. All right. Yep.
The phi minus 2 subscript.
Yeah, you can kind of consider that.
I mean, assuming you start with the scalar
Yeah,
one.
that's right. That phi minus 2, yeah, that for that case was like, I think, spherical coordinates, and I think we had a spherical object. So the solutions looked at 1 over r. But here we have an arbitrarily shaped object. Like it could be like starfish shaped or something like that. So it'll be whatever information is contained in that shape is in phi. We'll calculate it precisely for a sphere. But yeah, it's basically like you can get any number of solutions, but basically the one that contains the information that's linear with v vector, it has to be this vector. Yeah. Okay, so phi. Let's make this one. It's a function. Okay, so it's a vector function, just so you're nothing is a scalar. A vector function that depends on the geometry of the body. But not its motion. All right. So we've kind of decoupled the fact that we got basically two pieces of information. One, the shape of the body, which dictates the shape of the velocity field, but also the acceleration of the body, which is dictated by this v. V is function of t. And this phi only contains a shape, because this new equation, this new kind of like problem formulation, you see there's no velocity there anymore. We don't have any acceleration. This is just on the shape. All right. So the first calculation we're going to do is figure out what kinetic energy of the fluid is going to look like, and then we're going to take derivatives of that to understand. Look at the steady forces. And we're going to get a tensor. You kind of saw tensors coming up through the Navier-Stokes equations, where the direction also, like the forces depend on direction. And here you can imagine you've got bodies of different shape. The direction is going to be important. So the kinetic energy we'll call capital T. I think you can all remember this. This is basically the integral of 1/2 rho u squared, where you use the velocity of the fluid throughout the whole fluid. Okay. So using the notation that we have for irrotational flows, we'll replace u with del phi, and we'll also use a vector identity. So we're going to write this as del as phi del phi dv. Okay. And if you're not convinced that that's the case, you can do this yourself. You can take the divergence of this, and you're going to get basically del phi times itself, and also phi times del squared phi times del squared phi, which is 0 because of the definition of conservation of mass. All right. So let's pull the rho over 2 out because it's a constant, and so this is across the whole fluid. But we can basically do a generalized divergence theorem on this, where we basically take two boundaries, S and S infinity. S is the surface of the body, S infinity is like really, really far away. And what goes into that generalized divergence theorem is we're going to have phi and dot del phi. You can imagine I got this phi on the inside too, but because it's a scalar, I'm pulling it out. ds. Okay. By generalized divergence theorem. N is outward normal to body. All right. Yeah.
Kind of like saying you're integrating from the surface of the body to S infinity, or
Yeah, it's like, okay, I think I drew my arbitrary body before. So this is S, and then we'll have S infinity out here. And before, we were integrating through all this fluid, and I look at the boundaries of that fluid, I basically got these two boundaries instead. So I think any of you who've done this in undergrad, you probably just ignored the S infinity. You just did the S, which is basically like, I think if you did like, we did all these problems with divergence theorem. All right, so continuing. T is equal, so rho over 2. And we'll use this notation that integral n dot del phi, so remember n dot del phi, this is just, we can just call that d phi dn. ds. And you might ask what happened to the integral over S infinity, but at infinity the velocity is 0 because that was one of our conditions. Since d phi dn. Okay, so you consider that to be u goes to 0 as there. So the velocity goes to 0 there. And I'm using the notation. We have d phi dn is equal to n dot del phi. All right, I've got one. I got to make one sign change here. So this is divergence theorem is outward normal. Since we're in it, so in the past you've done it inside the body, but here there's outward normal to the fluid. Like the fluid's like your body. So basically, this is basically the normal vector that we need. I call that negative n, and so basically it's outward normal to the fluid, which is opposite of this. So we have a negative sign in front here. Because you can imagine it's like S infinity minus this thing, and then this we have this. All right. So basically the velocity goes to 0, but some of you might be really astute and say, hey, well the velocity does go to 0, but the surface area of that like outer surface goes as also goes as like the radius squared. So how are we gonna? The sum of that still might be finite. You could still have some like energy at that position. So if you want to be really careful, phi goes as 1 over r squared, then d phi dr, which is basically d phi dn, goes as 1 over r cubed. And so basically the integral of phi d phi dn ds, you're going to have basically a 1 over r squared, a 1 over r cubed, and times r squared, which goes as 1 over r cubed, which goes to 0. Okay. So if we keep on going, we got t is negative 1/2 rho, and then we have phi d phi dn ds. All right, how are we going to make this into a tensor? This is where the boundary conditions are going to come into play. So remember our boundary conditions. We've got phi is equal to basically v dot phi vector, and the boundary condition on the edge, the no penetration, says that n dot del phi, which is phi sub n, d phi sub n, that's equal to v dot n. Okay. So if we substitute those both into here, we get negative one half rho v dot v, and then v dot n ds. This is the boundary condition, and this is the definition. All right, now this is looking at something that can be more like a looking more like a tensor. All right, so you can consider this thing can be a tensor, where basically it's attacked by two sides by two vectors. So there's no dot here, ds dot v. I use the fact that I can switch the order. I wanted to contain the information of the body on the inside and the information of the velocity field on the outside. So in other words, t is equal to 1/2 alpha ij vi vj, where our tensor, where alpha ij is negative rho phi sub I. So remember, phi is a vector. So the ith component of phi, and we got n, which depends on the body's shape, across the surface area of the body. Okay. So this alpha ij is what we're looking for. So alpha ij is the added mass of the body. It's a function of the form only. So people ask you how much added mass, and you look these up in tables. It doesn't depend on how much you're accelerating it. It only depends on the shape, because the shape kind of dictates where basically the boundary conditions apply. And that's the boundary conditions are where we basically use the divergence theorem on. Okay. So there's no dot here. No dot. This is a tensor. So you consider it as like a 3x3 matrix or something like that in 3D. All right, this is kind of abstract, so let's actually calculate the added mass for a sphere. But the nice thing about this formulation, you could calculate it for like lots of different other shapes. I think they've calculated it for an ellipse, because you'd like to send elliptical things to the water because they're streamlined, and they calculated it for a sphere. But you could also calculate it computationally for any possible thing. So any questions about what I did here? Do people understand before we start putting some solutions in? Yeah.
Objects, you just have to know the function of the surface, right? Like different. That describes the surface of that object.
Yeah, you'd have to be able to solve. Well, you'd have to be able to solve Laplace's equation for the version that there's no velocity. Basically, you'd have to solve this one, and that will give you phi. Because phi is completely dictated by the shape of the body. And you'd also have to have normal vectors. So let's demonstrate with this sphere, because then we know both of those. For a sphere, we showed that with some work, we have phi looks like this. So a sphere moving at some velocity v. And using the formulation that we have above, that means the information for phi vector is just negative 1/2 a cubed over r cubed x position vector. Okay. And you can see in this case, the velocity potential due to the moving sphere at velocity v looked like this, and the phi vector has no information on the velocity field anymore. It's just basically the shape factor. So alpha ij, negative rho over 2. Maybe just substitute in here. A cubed over r cubed n x ds. So we can use the generalized divergence theorem for this part. Over 2. And this is on the sphere, the surface area of the sphere. So for inside the sphere, we lose the negative. Inside the sphere, we're going to lose the negative sign. We have gradient x dv and you also have that a cubed over r cubed is equal to 1, so that kind of factor goes away. And you have alpha being rho over 2, 4 pi a cubed over 3, which is the volume of the sphere, times gradient of x, gradient of the position vector, we've calculated this before, is this the identity tensor.
Why did you drop the negative sign again? For alpha ij.
Because this is the surface. Okay, so this is a sphere surface, and this is the volume. This is for the volume inside sphere. So there are kind of two ways you could do it. You could do n outward or n inward, and the direction of n will determine your if you're integrating the volume inside or outside the sphere. And we will do inside because that's easier. Yeah. 4 pi. Yeah, the volume of the sphere. So this is so physically, what is alpha? This is an isotropic tensor with magnitude equal to half the volume, half the mass of displaced fluid. Okay, so let's resolve the paradox of the bubble. And then we'll look at basically how we can show the steady force in this bubble 0. But that's kind of a longer calculation, so I want to do that at the end of rising bubble. All right, so now we know that basically, so we have this rho b, rho out here. It's rising with velocity v dot vector. Okay. Rho b, the volume. Yeah, I gotta have different v's. Oh, sorry. V u dot. Is equal to rho b vg plus. All right, so this was the bubble weight, which is pretty much nothing, right? And this is mass times acceleration, inertia. All right. So this is where our calculation now is is basically informed by our recent knowledge of added mass. So we're going to have these two terms. We have minus 1/2 rho v u dot minus rho g v. So this is the added mass. And this is the buoyancy. Okay. Sorry, this is not negative because it's added mass. Oh, wait, no. It's the same. It's basically like making your mass greater, so it is negative. So basically, v u dot is equal to, basically, we divide by our volumes again. You got rho b minus rho. But basically, the amount of mass you have is your rho b plus 1/2 of rho, because you're basically accelerating. This is basically accelerating half the mass of the displaced fluid. And if you calculate this is around negative 2g for air. Okay. And so bubble accelerates at 2g. I think so this resolves it, but we got to look at all. If we want to be really, really careful, we have to look at all the forces. That involves the steady forces and the buoyancy forces. Because here, this was kind of like this relied on some results that this had no steady force. But it turns out if you have irrotational flow, you don't have any steady forces. Like there's no drag forces with irrotational flows. So let's look at the whole force in the body. So remember, there's no viscosity here. So your stress tensor just gives you the pressure. Okay. But because our body's accelerating, we had to use time-dependent Bernoulli. And because if you're really, really far away from the body, the velocity is 0 and the pressure is 0, we're going to have this constant v 0 using condition at infinity. Remember, if you're irrotational flow, you can use Bernoulli equation between any 2 points in the fluid, not just along the streamline. All right, so we're going to substitute this into that integral and try to solve. Phi So this is our phi, and we're going to substitute this into, so we got to figure out the this unsteady force and the steady force part. All right, so this is where things get a little hairy, because you're basically going to have to use chain rule, because the velocity is a function of time, but also your velocity of the fluid is a function of time, because that's influenced by the velocity of the body. Why don't I let you try to calculate this on your own based on what's above? I don't think we only have 2 minutes left. I don't think we're going to be able to finish it. Oh, 30 minutes left? Oh, then we'll be fine. Sorry. All right, then we're definitely going to finish it. All right, so v dot. So chain rule. First we got v dot phi vector, right? And the second one, all right, the body's moving at something that's changing the time. So that's going to give us a chain rule, so minus because of that. And then we have the derivative of x dot dotted with the fact that we took the gradient of phi from the outside. All right. And the fact that we have this v that's going along with the ride. Okay. So this thing is gradient of normal original phi, not phi vector. So we put these together. We get v dot phi vector. We just copy from the top minus v dot grade phi, right? And we can do one more step using the fact that this is using the fact that this is equal to our velocity field. So we have v dot phi minus dot. All right. So we wanted to figure out what the derivative of the potential was with respect to time. And we had to throw this thing in there, and we got two terms because we got two functions, the velocity of the body and how much the position of the body changes because of that. And then we got these two, where u is the velocity of the fluid, v is the velocity of your body.
And that's the vector phi by the dotted.
Yeah. Sorry.
It gets confusing fast for me.
Where does the grad phi come from? In the second one?
This here?
Above. The grad big phi.
Here? So phi is not a function of time. Phi is a function of space. So the space is a function of time. So basically, if you take the derivative of d, it's like the chain rule. It's like the one-dimensional version of this would be d dx of f of g of x. It'd be df dx, and then times dg dx. So basically, we got to take the derivative of that, and then you got to take the derivative of the stuff inside. This is the chain rule. Where in this case, it's basically like the time is only there because of the stuff inside the parentheses. All right, so together we got basically P is equal to rho times, let's just substitute this in. V dot phi vector minus v dot u. So I'm just substituting. Actually, let me just write the original one so we don't get lost. So the original one from Bernoulli was p equals negative p is rho d phi dt plus 1/2 rho u squared plus rho g dot x. Is it plus or minus in the first one? Yeah? Oh, okay. V is the velocity of the body. U is the velocity of the fluid. And we're just using the fact that potential flow. Oh, this is not very good notation. We're using the fact that in potential flow, this is equal to this. Okay, I gotta fix a sign error here. All right, so psi. I think this. Right. Let's leave this plus for now, because I think it's from what we derived a few times ago. It was basically plus rho g dot x. When we calculate the buoyancy force, we'll see if it needs to be fixed. But basically, what I have for the time-dependent Bernoulli equation is the rho. I have this thing above is only a function of time. So this is from what we had last time. This is only a function of time, but basically at infinity we have 0, so this is going to be just 0. All right. So, and let's substitute this in. So this is rho v dot phi minus rho v dot u plus 1/2 rho u squared plus rho g dot x. All right, so we got to calculate each of these things. Physically, this is the steady force. Steady state force, even though you're accelerating the body, you still have some instantaneous velocity of the fluid that you can calculate in a point in time. And this is basically the contribution, the steady part of the force that you're feeling on the body. This part is basically due to your v change at the time. And this part's your buoyancy. And we've calculated this last one in terms, so let's just review. Let's consider each force in turn. So we calculated this before. So the buoyancy force FB rho oh, there's a negative sign here. All right, so this negative sign means that I've got to actually integrate negative pressure. So we'll put that negative pressure n hat ds, okay? And so, sorry, there's no rho. So negative, we have this, and that gives us this. So we have rho g dot x n hat ds, okay? All right. So remember, you did this on the homework, and you used generalized divergence theorem. We'll pull the rho out, and you showed that by generalized divergence theorem, this is del of g dot x. Where there's no dot, it's del g dot x. This is what you did before. dV. There's the volume. And then this was, you showed that this was a rho g integral of your body, dV, v, right? And so this is rho g volume of the fluid. So the buoyancy force is proportional to the volume of your displaced fluid. Volume of displaced fluid. All right, so that is that should be a review from what we did last time. All right, now showing that the steady force is 0. That takes a little work. So let's talk about this. Yeah.
What did you just change there? You changed something to a negative?
So
Up where the,
this is the force in the body is negative pressure, where basically this is the outward normal. This is the definition. This is the definition by definition of the stress tensor, and that's because we consider n had to be into the fluid, so we have this negative sign here. So I have the negative p, and I copy that negative p from this thing, and that's just rho g dot x. Yeah, this one is plus rho g dot x. I think originally I had a negative, because it all depends if you want to keep your g, your sign in your g, or outside your g. But I think it's least confusing to keep it inside the g. But honestly, even after all that work, I think I'm still off by a sign, because buoyancy force should be going up. And here we have, well, del, okay, well, this is g. This is going down. So somehow it should be going up. But you did this for the homework, so you can probably figure out from your old homework. Steady force, Fs. All right, so now we got to consider the steady force, which is basically two terms. The steady force, if you remember, basically, we're going to be integrating. We have basically these two terms. Pressure is equal to P steady. I don't know if that's good notation, but there are these two terms in the pressure equation. You had negative rho v dot u, and also 1/2 rho u squared. And we had to show that both of these go to 0. The sum of these two go to 0, integrated across the thing. So let's consider the second one first. So let's use generalized divergence theorem here. So this is on the surface of a body, on S. And if we do the fluid volume, that's gradient of, and let's take out the rho, because now I carry the rho around everywhere. So let's take out the rho. This is del of u squared over 2, and we'll substitute the rho at the very end. dV, right? All right, and we've used this identity before. We use this when we derive the Bernoulli equation. All right, d volume. So let's go term by term to figure this out. Okay. First of all, because it's irrotational, this is going to be 0. Okay. And then we can write this next term here as using the identity del dot uu minus u del dot u. Okay. But because of conservation of mass, so there's a dot product there, this is 0. So this becomes del dot UU. Which you can write as a integral of n dot UU. And we can do a substitution because we're talking about the surface of the sphere. We can write this as n dot v u ds. Okay. By star. So star is the boundary condition. Is a boundary condition on the surface. Which says that no penetration. U dot n is equal to n dot v. The velocity of your body dictates the velocity of the fluid, but only in the normal direction. This is no penetration, not no slip, because we actually have slip in potential flow. All right. So the steady force, we got this. Let's add these two together. We got rho n dot v u minus n v dot u, which we have. This is the first term that we just calculated, and this is the second term, ds. And this is integrated over the surface. Rho divergence of so we first do a divergence theorem to translate it back to volume coordinates. Then we basically pull this derivative inside. Plus v dot del u minus, and we keep the other side the same. dv. Okay. The velocity of the body has no function of space, so this is going to be 0. And then the rest of it is index notation. Why don't you see if you can do the index notation on your own, and then we're going to review it. This is where you can talk to a partner next to you. So remember, this is the velocity of this is the velocity of the body, and this is the velocity of fluid. So each of them is going to have each of these gradients are going to have a different a dx dj because the gradients depend on direction too. So why don't you see if you can write the index notation, and let's see what we can get. And I think that'll be the last thing, probably the last thing that we do, but. This is kind of independent part of what we did previously. So every time you have a new variable, introduce new index. All right. So we got row, angle. And the dot products are going to basically, you think you have 3 indices, but the dot product will give you 2 indices because the delta. And you're stuck, talk to the person next to you. This will be good. I mean, technically, the index notation on the quiz is going to be it's basically just definitions. All right, so remember, this gives you a tensor. Del U gives you a tensor with two indices, right? But basically, the V kills the first index. So this first term, you're going to get V. Let's call it Vj, Ej, and then this one's going to give you some. But basically, the dot goes with the gradient of 1. So this will give you dui dxj, right? And this will be ei, because that's the only one that's left. So this Vj goes with the dxj, because that's where the dot is. And then we got minus gradient of this thing. So ei ddxi of Vj uj, which is the dot product of V and U. All right, dv rho. Let's simplify a little bit. We got Vj ei dui dxj minus duj dxi dv. Okay. Well, this thing is equal to 0 since irrotational. So the curl is 0. Okay. So this gives us our most general form of D'Alembert's paradox, with a lot of a decent amount of manipulation. It basically says if you've got a accelerating body, like a body, so what you're doing in the homework is in some ways easier. It's showing the steady force on a cylinder is 0. But this, we didn't say anything about a cylinder or anything. We just said an arbitrary shape. The general formula, basically the steady forces vanish, and because it's irrotational. So when you have something that's irrotational, you just cannot have what you call drag flow. And in this case, even the body was moving unsteadily for unsteady motion. All right. So the acceleration. So all right. So to review, we basically got p is equal to we had negative p is equal to rho. So I'm just going to rewrite what we had before and relabel these things. this was the unsteady part. Here, let's just kill this bracket. Rho. And this was the steady part. And this is the gravity part. All right, so what we calculated was this was the steady force, what we called Fs, steady force, because this was the time-dependent part. This is the acceleration force, Fa, and this was the buoyancy force. All right. So we showed that the steady force was 0. We said this was basically equal to rho gv. Actually, negative is supposed to go in the opposite direction. It's supposed to go opposite of gravity. And this one is we're going to calculate this one right now. So this one, Fa, equals to rho v dot phi n. All right, so let's just slow down. So this one is okay, we got negative p n hat ds, right? So you're going to have rho v dot. So we're going to substitute from up there. V dot phi n hat ds. But basically, this v is doesn't depend on position. That's just the velocity of your body. So this is rho v dotted with phi n. Hat ds. All right, and this was our added mass tensor. Yeah. So that's our added mass tensor. So basically, we got rho v dot. I think this is not great notation, but I think I called it alpha ij. That just depends on shape. Just depends on shape. All right. So, in all, that's why basically, when you look at a rising bubble, if it's irrotational flow, you have no steady force. All you have is basically the buoyancy force, which pushes it up, and the added mass force, which is basically putting kinetic energy in the fluid and keeping it slow. And when you have a bubble rising, in general, when you have any body that's really, really lightweight compared to the fluid, the added mass is dominant. So that means for bubbles or those like insects walking on water and stuff like that, basically it's the fact that you're moving like an air pocket and you got to move fluid to fill that air pocket space. And we showed for a bubble that this gave you a factor of I think it was 1/2 v bubble for sphere. That was the dominant thing for the sphere. If you're basically your body is really, here, let's just write it down. Added mass is important for lightweight bodies. For bubbles and other lightweight bodies. The reason why they're important for lightweight bodies is because their regular mass is like negligible. Like they don't actually weigh anything. So you would think they'd have like, huge speeds because they don't weigh anything. And F equals ma will say that A was going to be ridiculously high if m is small. But they start to become important. But here you got 1,000 times heavier fluid, so then you actually have to calculate the kinetic energy of the fluid. And we basically showed that if you have this rising bubble and you have all this kinetic energy, that this is equivalent, so bubble rising. And we know we have these flow fields. We have basically these velocities. We basically showed that this is equivalent to basically, a bubble dragging. It's like dragging like a half sphere. Oh, this is going to be kind of ghetto. This is a half sphere of water in tow. But basically, all the kinetic energy of the fluid is equivalent to dragging half a sphere of water behind it. That's the cost of moving all the fluid from here to infinity. We were able to calculate exactly because we knew what the potential was exactly for a sphere. And I think your approach for the homework is actually much similar to this, but this is the general idea. All right, the last question of homework involves velocity potentials and stream functions. We're not going to be able to get to it today, but we're going to do this idea of complex potentials next time. Basically, W of xy is going to be a complex number that's going to have as its real number the potential and as its imaginary number the stream function. This is called the complex potential. But otherwise, you solve problems very similar to the way you did in undergrad with regular potentials. It just allows you to get the potential and the stream function, the streamline, all in one go, as opposed to independent calculations. So we'll talk about stream functions and potentials next time. I'll sketch you out a few common ones, like a uniform flow at an angle, irrotational vortex, which you kind of need for doing the last ones on the homework. I think I sketched you the irrotational vortex even before we got to complex potentials a few times ago. But we have the students to entertain on Monday, so we'll do some of that then. And then we have the quiz on Wednesday, so I'll probably have the homework due like the week after, where we'll definitely finish complex potentials. Because you pretty much have everything you need to know to do all the homework except for one problem. So it's not going to be, homework's going to be due not next week, but the week after. And also remember your course projects. We only have I think 4 lectures left before Thanksgiving somehow. Is that true? Yeah. And then after Thanksgiving, we have course projects. So I've only been able to teach you this much in the course. That's why they call this Introduction to Fluid Mechanics. But I think we'll definitely be able to have enough for the last that homework. I don't know if we'll have enough for another homework. We'll have to see. Okay, I think I'm going to have office hours until 1:30 if someone needs me, and then I'm a little bit free after 2:30, just a little bit. But otherwise, we can have our usual hours. Usually people want to meet the week stuff's due. Today I don't think I can do 7:30. It might be a little tight. I might be able to do late, but that's getting kind of late. And if you came in late and didn't get your candy, stop on and get some candy. I don't think so, actually, because our time-dependent Bernoulli equation has an inertia term. That's where you get the rho u squared, the kinetic energy. You don't have Bernoulli at low Reynolds number. There's some other tools for low Reynolds number, but I don't think I've never heard it for low Reynolds number.